Hey folks, so I want to do an example of computing and interpreting a confidence interval for a difference in two population means. And this is from chapter 6.7, and I'm going to do a problem from the textbook. I have the formula written up here, and what I've got, where the pen is pointing, that is the point estimate for the difference in population means that is based on the difference of sample means. After our plus and minus sign, all of this is the margin of error, right? And that margin of error is composed of, first there's the t critical value multiplied by the standard error. And this is the standard error for the difference in two population means. So let's take a look at the textbook and take a look at this problem. Okay, so we've got, don't know how to pronounce this, prothrombin time is a measure of the clotting ability of blood. For 10 rats that were treated with an antibiotic and 10 control rats, the times were reported as follows. So we've got two groups here. We've got the time in seconds for the blood clot time for the treatment group exposed to the antibiotics, and then also the control group. So we're going to construct a 90% confidence interval here. This is for the difference in population means. There's a note here. Remember, there's a kind of an issue with degrees of freedom, like what are we going to use? They are saying that this formula, that really intense Welch, Satterthwaite, degrees of freedom formula. They computed that for you because it's obnoxious, and that's the degrees of freedom that we'll use. Okay. So we've got all the elements in place here, right? We've got our sample size. Whoops. We've got our sample size. It looks like it's 10 in each group. It's not required that they have the same sample size, but that's coincidental here. We have the sample mean for each group and the sample standard deviation. So we've got all the elements that we're going to end up utilizing in our formula, but we do need to take a moment to figure out what this t critical value is. We're going to go use the t-table to find that, and I'll also show you how to do that in R. So we were told that degrees of freedom is 17. I think it was 17.2. If we're using the t-table, it's only got integers, so I'm just going to write 17. In R, I'll go ahead and write 17.2. The confidence, 90% confidence, that is referring to this t-distribution with 17-ish degrees of freedom and 0.90 in that middle area. 0 is in the middle. This t critical value is this tick mark. What is the area to the right of that tick mark? Well, alpha is the complement, right? 0.10. So 0.10 is the area in the tails. But there's two tails, symmetric. So in each of those little regions here, I'll do green to match, is 0.05. In the t-table, therefore, we're going to go to the row that says 17 and the column that says 0.05. let's go find that number. I'm going to open up my t-table. That upper tail probability, 0.05, and I'm going to cruise down to 17 degrees of freedom. Here we are. So that is the number that we're going to use to compute this confidence interval. That is the t-critical value. 1.74. If we wanted to find that in R, we would want to use let's think about it, or we would want to use the QT or the PT function. Well, remember PT or P-norm or P-binom is a tool used to find probability, P probability. We don't need that, right? We already have a probability that was implied to us, that 0.05. I should label this 1.74. What we were searching for was not a probability, but a t-value, a tick mark here. So we want to use QT. And the input for QT is kind of the, I'm going to say left-sided probability, comma, degrees of freedom. If we type that into R, let's see what we need to type. Well, we were given degrees of freedom, 17, we'll go with 17. I guess the book said 17.2. We can do that with R. The table only has integers. Let's think about what is the probability or the area to the left of this blue tick mark. Add them up. The area to the left of this blue tick mark is not 0.05, not 0.90, but 0.95. So let's go cruise over into R and see that when we type this QT function in, that we get something pretty dang similar to 1.74. All right? It's not going to be exact, but it should be pretty dang close. I've already got some stuff written here, so I'm calling this T-crit. Aye. And there it is. So I actually typed 1 minus 0.05 just for my own brain there. But we got from R 1 point, pretty dang close to 74. 1.7384444444. That's good enough. Now we've got all the elements to plug into our formula up there in purple. So I'm looking at our sample statistics, getting ready to plug all these components into this formula. So I'm going to start with the antibiotic group as group number 1. Sample mean, 25. We're going to subtract the mean from the second group, the control group, 23. So I'm going to add, subtract to our T critical value, which is approximately 1.74. And then this is going to be multiplied by that standard error, S 10 squared over sample size 10 plus S for the control group, 8 squared over its sample size of 10. I'm going to get R to help me to compute this. We could do this in one fell swoop, but I'm going to do it step by step. I've got the standard error here already waiting. So square root 10 squared over 10 plus 8 squared over 10. Tell me what that is, R. Okay, so that is a 4.049691. I can do this subtraction in my head. I think that's a 2. I'm going to take that standard error and multiply it by the t critical value. So that is a margin of error of about 7.04-ish. And now we can perform the subtraction to get the lower bound and the addition to get the upper bound. I could probably do that in my head, but I'm going to use R to help me with this. So I've computed the lower and the upper there. So hook it up, R. Lower, upper. Tell me what those values are. A negative 5.04 approximately to 9.04. And this was in seconds, right, for the clock time. So there's our 90% confidence interval for the difference in mean clot time between the antibiotic group and control group. We're going to interpret this interval in a moment, but part B of this problem asks, why is it important that we assume that the two populations are normally distributed from part A? So reflect back on the requirements in order for this process to be valid. One of the requirements is that the two samples have come from normal distributions. But if that cannot be met, then we can use the central limit theorem as a backup. Here, it is required that both populations are approximately normal because the sample sizes are small. And by small, I'm really saying less than 30. If the sample sizes were at least 30, I guess this should actually be a strict less than. If the sample sizes were at least 30, then the underlying distribution from the population isn't too important for our purposes. Let's look at part C, interpretation. So something to notice with our confidence interval from above. The interval spans from about -5 to +9. What value is important when we're talking about a difference between two things? That value is 0. This confidence interval contains 0 between its bounds. Since 0 is contained within the confidence interval, that implies that there is no significant difference in the average or mean clot time between the antibiotic group and control group. Again, this is because 0 is within the confidence interval, implying that there is no difference. Now, it's not a proof that there's no difference. It's evidence to support that. And this is also about the mean clotting time. The mean clotting time. Population mean. Okay, hopefully this was valuable for you.